Welcome! In this video, we will go through and demonstrate the major enhancements of ANSA version 25.0.0 in the field of occupant safety. Starting off with the dummy articulation tool, users can now accurately adjust the position of the IR track mechanisms of Thor 50 ATD. This is made possible through introducing a separate tab in the tool, called IR track. For this demonstration, the Thor 50 ATD has already been loaded inside ANSA. Go to Safety, Dummy, Articulation to open the Articulation tool. Once opened, navigate to the IR Track tab. The tab is filled out with the model's identified IR track mechanisms. If no mechanisms are identified, the tab is grayed out. Left-click on a mechanism to select it from the list. Adjusting the mechanism's position can be done either by directly defining the total elongation value or by incrementally moving the mechanism. This is done by defining the appropriate step value and pressing the plus or minus buttons accordingly. Moreover, in the Dummy Articulation tool, it is now possible to save a position's parameters and reload them later to instantly position any ATD. Start with a position dummy. Select the POS file write option to write out the JSON file. Name the file and select where it will be saved. For demonstration purposes, return the dummy to its initial position to read the .json file. Click and hold on the POS file button to select the read option. Select the file. The dummy is now positioned. Moving on to the Human Body Model Articulation tool, where several updates have taken place in this ANSA version. Starting off, users are now able to calculate the initial joint angle parameters for thumbs models. This ensures accuracy during input for crash simulations. To open the HBM Articulation tool, go to Safety, Human Body Models, and Articulation. To use the tool, make sure to load the proper metadata file that corresponds to the used HBM. For the demo, start with a position thumbs model. Click on the Output button and select the angle parameters from the drop-down menu. Select the input file. Once read, the parameters are calculated and displayed under the Preview Results section. To output these results, click on the folder icon. Name the file and press OK to confirm saving. Moreover, a tab dedicated to handling all spine movements has been added in the HBM Articulation tool. This tab allows precise spine manipulation by enabling individual spinal movements. Let's have a look at the new Spine tab. To use the tab, make sure that the metadata file contains individual spine movements. The Spine tab can be broken down into two sections, the Visibility Options section and a table-like section, responsible for assigning spine movement. Each row corresponds to a specific vertebra, and each column corresponds to a specific type of movement, a rotational movement around the X, Y, and Z axes and a translational one along those same axes. Let's isolate the skeleton through the visibility options to better overview spinal movement. To position the spine, start by defining the way motion will be applied through the Apply All flag. When enabled, movement is not applied directly and can only be applied by pressing the button. When disabled, vertebrae are positioned immediately with each change. Keeping the flag enabled, define the step that will be used. Select the vertebra which will be moved and the desired movement. By using the arrows inside the cell, the rotational or translational magnitude can be applied incrementally. Final magnitude can also be assigned by direct value definition inside the cell. When done, press the Apply All button to apply movement and position the spine. Let's demonstrate positioning with the flag option disabled. Similar to before, adjust the assigned value using the arrows inside the cell or by directly typing it in. This directly implements motion for each vertebra. As demonstrated, motion can be implemented for multiple vertebrae even if the positioning is directly implemented. Additional updates on the HBM articulation tool also include combining flexion and extension movements in a single button in the Biofidelic Moves tab. This simplifies the interface, making it more intuitive and user-friendly. Let's navigate to the Biofidelic Moves tab of the HBM articulation tool. Each movement is described by its own button. To provide an example, let's select the knee_left movement, responsible for articulating the left knee. Both positive and negative total angle values can be assigned, performing both extension and flexion of the knee. Adding a flag option in the Rotate tab enables the simultaneous and symmetric articulation of the legs, establishing more uniform torso mesh deformation, and generally improving the metadata input performance. Let's demonstrate how to use the Both Legs option in the Rotate tab. Scroll down to locate the acetabulo-femoral joint tree motions and select either one of them. Once selected, the Both Legs flag can be activated. Activating the flag will merge the two separate joints into one, as evident also in the tab and graphical user interface. Then, users can proceed to articulating the legs as normal. In this instance, the total angle has been directly defined and applied. Articulating both legs simultaneously results in smoother torso mesh deformation. A lock icon has been added into the seatbelt tool. This lock option allows users to maintain the seatbelt's elements when editing a component. To open the tool, go to the Safety ribbon, Occupant, and select the Seatbelt tool. To demonstrate this feature, a seated dummy with a created seatbelt will be used. Keeping the lock option disabled while selecting the interactive option allows interactive edit. However, when lock is enabled, the functionality is grayed out, thus allowing only to stretch or move the component without recreating the elements. This maintains the same element IDs on the final seatbelt component. As demonstrated, the difference between the starting element length and the final one is minuscule. Finally, the Seat Positioning tool now supports the definition of a custom seating reference point to select the starting position of the seat. Prior to this enhancement, it was automatically assumed that the seat was always in the design position, known also as point A of the seat's field. To open the Seat Positioning tool, go to Safety, Seat, and select the Positioning function. To demonstrate this, start by loading a seat file in ANSI version 25. Open the Seat Positioning tool and select the desired positioning protocol as per usual. Select the seat field's PID. As in previous versions, this automatically identifies the seat field's points coordinates. To define the seating reference point or SRP, enable the flag option. Once enabled, the X, Y, Z coordinate fields can be filled in. This can be done either by direct value input, creating a preview of the SRP point in space, or by pressing the F1 button on the keyboard inside one field to select a point from the screen. A preview of the SRP point is created here as well. This concludes this video. Thank you for watching.